In this second video for Chapter 8, we're going to look at four types of integrals that involve powers or integrating powers of trigonometric functions. So let's look at the first type next. So first we're going to look at integrals that involve even powers of sine and cosine in written form or in integral form. We're looking at integrals like this, where the power on the cosine and the power on the sine are both even. So let's look at a particular example of this, example 1 from page 116. So we're looking at this example where both sine and cosine are to an even power, the power 2 under the integral sign. To do integrals where the powers of both sine and cosine are even, we need to use these two identities, because we cannot integrate cosine squared or sine squared directly. Throughout this chapter, when we integrate these powers of trig functions, we have to convert the powers some way, because we don't have a product rule for integrals. The integral of cosine squared x cannot be integrated directly, nor sine squared x. So we have to have a strategy for converting them to another form. So when both powers are even, we need to use these two identities here. These are not the typical identities or the familiar identities for cosine squared x or sine squared x. Normally we'd write cosine squared x as 1 minus sine squared x, and sine squared x as 1 minus cosine squared x, but here we use these two identities. So if we go back to the integral that we started with, which is cosine squared x times sine squared x dx, and we replace cosine squared and sine squared with these two identities, we are integrating this. And so let's simplify that on the next blackboard. So we're going to multiply the 1/2 times the 1/2 and bring that out front, and then we're going to multiply this a plus b times a minus b to get this. So we're stuck in the same way as we were originally. We have the cosine to an even power, and we have to get rid of that even power. So we're going to use the same identity that we used before to convert this to cosine without the power being squared. So first we split it into two integrals. The first integral is, of course, easy to do, 1/4 x. And then we apply this identity here and in a slightly different way. We notice that when we have x on this side, we have 2x on the right side, and in this case we have we're starting with 2x, and so we're going to wind up with that identity applied with a 4x resulting. So it's 1/2 1 plus cosine of 4x dx, because the angle 2 is doubled to a 4. So if we distribute this 1/4, we're going to get 1/4 x minus 1/8 integral dx, and then minus 1/8 integral of cosine 4x dx. So let's pick that up on the next blackboard. Let's note that when we integrate cosine of a constant b times x, we are letting u equal bx, du is b dx, du over b is dx, and so if we convert to the variable u, we have 1 over b integral cosine bx dx, which is 1 over b and then we get what? Sine bx, excuse me, we get 1 over b sine of u, but u is bx. So it's sine bx over b is what we get. So in this case, in the one we're working on, it's 1/4 x minus 1/8 x minus 1/8 times cosine 4x over 4, because the b is 4, and then we just need to combine terms. There's actually a mistake in the book, which has a plus sign here. It should be a minus sign. So when we combine terms, we get a 4th minus an 8th, a 4th x minus an 8th x, which is an 8th x, and then minus cosine 4x over 32 plus c. On the next blackboard, let's take a look at a second example of an integral of this type. So just like before, we are applying the identity here involving cosine squared x, and when we do that, we get we have to apply it times itself. So 1/2 1 plus cosine 2x times 1/2 1 plus cosine 2x, because we need to rewrite the original integral like this, so that we can break it down into powers of trig functions not involving a square. So we bring the 1/2 to 1/2 times 1/2 out front, and then we are foiling 1 plus cosine 2x to get 1 plus 2 cosine 2x, and then plus cosine 2x times itself, which is cosine squared 2x. Now we can break this, or we want to break this down into 4 or 3 integrals: 1/2 1, or 1/4 dx plus 1/4 times 2 times cosine 2x dx plus 1/4 cosine squared 2x. And we are able to do these first 2 integrals without any further changes, but for this third integral here, we have to apply the identity for cosine squared once more. And so we're going to rewrite what's under the integrand here as 1/2, and remember, we're doubling the angle, so again we get 1 plus cosine 4x for cosine squared 2x. So let's pick that up on the next blackboard. So let's note that we're distributing this 1/4 here across this 1/2, and we're creating this integral and this integral are staying the same, which is here and here, and then we've got the 1/4 across these 2 new integrals here. So we can integrate everything now, and then we'll just have to combine terms to get a result. So it's 1/4 x plus 2/4, which is 1/2. Integrate cosine 2x and get sine of 2x over 2. Integrate this distributed across, and we get 1/8 x, and then we integrate this 1/4 across here, and we integrate this 1/4 across here, and when we do that, we get 1/8 times sine of sine of 4x over 4 and plus c, and then we're going to combine everything together to get this. So this completes the second example on page 166. Now there's a third example of this type in your text on page 167. I'm going to leave that to be one that we can that you study on your own. This would be a question that could appear. This example 3 on page is one that could appear on the test, but usually I consider that one to be too hard to be on a test unless it's an extra a question that you get some extra points for. So let's now go to the second type of integral that involves powers of trig functions, where we have cosine to the mx sine to the nx dx, and one of the powers m or n is odd. In this case, the integrals actually are quite a bit easier than they were in this first type we looked at, even if the powers are quite large, as we'll see with this example 4 on page 167. So before we start looking at the technique for doing integrals of this type, might be good to stop the video for a minute and take a little break, as it's going to take about 6 or 8 minutes to go through this type, and we have several more types to go. So let's assume that you're back now after a little break, and let's continue this integral on the next blackboard. So when we have one of the functions sine or cosine appearing, at least one of the functions sine or cosine appearing to an odd power, we can do this. We can separate off a cosine x dx, in this case coming from the odd cosine cubed x. So we're splitting the cosine cubed up this way, and the reason we want to do that is that this cosine x dx can be du, with our u being sine x. So our u equals sine x, and then our du equals cosine x dx. And when we do that, we see that we get a much simplified integral. In fact, an integral that's easy to do and only in the variable u. So the sine to the fourth becomes u to the fourth. The cosine squared we write as 1 minus sine squared x, and so that part of the integral becomes 1 minus u squared, and then, as we've already said, the cosine x dx becomes du. So we have a much easier integral, an integral only involving powers of u, which is easy to do, especially when we realize it can be written as u to the fourth minus u to the sixth integrated du, which is what u to the fifth over 5 minus u to the seventh over 7, and when we convert u back to sine, we get sine to the fifth x over 5 minus sine to the seventh x over 7 plus c. So pretty easy, right? And then if we continue with another example of this type, example 5 on page 168, well, this time we have both the cosine and the sine to an odd power. So we could either separate off cosine to be a du or separate off sine to be a du. We're going to choose to separate off the sine. So we're going to rewrite this as cosine to the seventh x, sine to the fourth x, sine x dx, and the sine x dx is going to be the du, or actually the minus du, because u is going to be cosine x, so its du is minus sine x, and minus du is sine x dx, and so we immediately get that cosine to the 7th is u to the 7th. It's a little bit more work to get sine to the 4th. We have to write sine to the 4th as 1 minus cosine squared x squared, which gives us, when we convert to u, 1 minus u squared. Squared du, bring the minus sign out front, and so it's still just integrating powers of u. This should be a squared here. We have a little bit of algebraic work to sort it out. So 1 minus u squared squared is what? 1 minus 2u squared plus u to the 4th, and we're going to distribute a minus u to the 7th across that, so we get what? Minus, let's leave the minus sign out front of the integral, so we get what? U to the 7th minus 2u to the 9th. So minus the integral of u to the 7th minus 2u to the 9th plus u to the 11th. We're going to integrate and get minus u to the 8th over 8 minus minus, so plus 2u to the 10th over 10 plus u to the 12th over 12 plus c. And when we convert this back to cosine, since u was cosine, we get cosine to the 8th over 8 minus cosine to the 10th over 5. So cosine to the 8th x over 8 minus cosine to the 10th over 5 plus cosine to the 12th over 12 plus c. So even though the powers were quite large on this, it still just turned out to be powers of u that we were integrating. So we're just integrating powers of u, and or at least once we convert it over after a couple of steps here, we're just integrating powers of u, and so then it's a pretty easy, or actually very easy, integral to complete. So there is one more example, example 3 on page 167, where we're integrating sine to the 6th, and we have to rewrite that as 1/2 1 minus cosine 2x quantity cubed. There's a lot of algebra involved in that, and so I'm not going to complete that one. As I said, it's a little too hard, except as a bonus question on the test. So now we're going to go to the third type of integral, where we're integrating powers of sine and cosine. Again, it would be good for you to take a little break and come back to this when you're ready. I'm sorry, what I just said was wrong. That example 3 on page 167 is for the first type. All of the integrals of this second type, type 2, are just as easy as these. Maybe the algebra can get a little bit more complex, but generally they're pretty easy to handle. So type 3 coming up in just a minute after your break. Okay, so our third type of integral involving powers of a trig function involves powers of secant and tangent. The first case we're going to look at is when the secant is to an even power. And so when the secant is to an even power, we're going to be able to split part of that off into secant squared x, which is going to be or secant squared x dx, which is going to equal our du. And so let's look at an example of this. Example 6 on page 168. So we see that secant is to an even power, and that allows us to rewrite the integrand in this way. So we have separated off the secant squared x. That becomes our du. Our u becomes tangent of x, whose derivative is secant squared x dx. And so the integral turns into tangent to the fifth becomes u to the fifth. Now we probably don't remember this identity so well involving secants and tangents, so let's show how to get it. We know cosine squared x plus sine squared x equals 1. Of course, that's easy to remember. If we divide everything through by cosine squared x, the first term becomes 1. Sine squared divided by cosine squared is tangent squared x, and that equals secant squared x, 1 over cosine squared x. So that allows us to convert secant into 1 plus tangent squared. And so so let's write the secant squared here as 1 plus tangent squared x, and so that turns into 1 plus u squared, and we have already said that the secant squared turns into du. So our integrand is powers of u, which are easy to integrate as what, u to the fifth plus u to the seventh du, and that gives us u to the u to the sixth over 6 plus u to the eighth over 8 plus c, which is tangent to the sixth over 6 plus tangent to the eighth over 8. And so a pretty easy integral to do after we certainly after we make the conversions. Example 7 on page 169 is just a slightly more complex example than this. It's just that the algebra is a little bit more complicated. The conversion steps are still the same. So let's look at the final type, type 4 of integrals involving powers of secant and tangent. Again, it would be good to take a little bit break and come back to this final example for this chapter. So in this last example, we note that we have powers of tangent and secant, and the secant is to an odd power. So let's see what we do in this case. I said something incorrect. This is example 7 on page 169 that we're doing now. There's not a second example of type 3. So in this case, both the power on the tangent and the secant are odd, and then we are able to convert the integral to another to one that's powers of u. So let's see this example. So in this case, we are going to separate off secant times tangent to be the du. So it remains, or what remains, is secant to the fourth, tangent to the fourth, and then we have secant x, tangent x dx. So that secant x, tangent x becomes our du, and our u is secant x, whose derivative is secant x tangent x dx. So let's see what we have then. let's go back to this identity, which written in another form allows us to write tangent x, or tangent squared x, as secant squared x minus 1. And so that allows us to write this integrand as secant squared x squared, which is, I'm sorry, that's not right. We want to convert the tangent squared to tangent squared x squared, which is going to be secant squared x minus 1 squared. So when we convert everything over to u, the secant to the fourth becomes u to the fourth, and the tangent to the fourth, because it is secant squared x minus 1 squared, is u squared minus 1 quantity squared. And so the integral is just that. U squared minus 1 quantity squared coming from the tangent to the fourth, u to the fourth coming from the secant to the fourth, and then the du coming from the secant x tangent x dx. So we pick that up on the next blackboard. So we expand u squared minus 1 and get u to the fourth minus 2u squared plus 1. We distribute that across u to the fourth and get the integral of u to the eighth minus 2u to the sixth plus u to the fourth du, and when we integrate that, we get u to the ninth over 9 minus 2u to the seventh over 7 plus u to the fifth over 5 plus c, which of course is secant. U is secant, so it's secant to the ninth x over 9 minus 2 secant to the seventh x over 7 plus secant to the fifth plus secant to the fifth over 5 plus c, and so there is our answer. So we've discussed these four types. Let's just very quickly go back through the four types. In the case when both the powers of sine and cosine are even, we use these two identities right here to convert all of the powers of sine and cosine to powers that aren't even any longer, and then we're able to integrate them. In the case when at least one of the powers of sine or cosine is odd, we separate off either cosine x dx or sine x dx and make that a du. Then there are two types of integrals involving secant and tangent. When the secant is to an even power, the secant squared x dx is separated off as du, and when the secant and the tangent are both to an odd power, the secant x tangent x becomes the du, and secant becomes the u. So these types of integrals, once you have straight what the substitutions are and what becomes the du, are relatively easy ones in this section. This will conclude this video on section 8.3.